Good morning, good afternoon, or good evening. We're now on the final question of the Step 3 2024 paper, our final stats question. As mentioned in the previous stats video, I did find much more success with the stats questions than the mechanics, and although it's not something we cover the further statistics, it'll be worth looking at both the discrete and, for this question, the continuous probability distribution ideas in the further statistics. I feel like they are relatively simple and use a lot of the pure ideas that you have. So jumping into this question, we have a particular picture that we need to draw. We have a pen that doesn't want to work to start with. Let's try and give that a quick reset. Okay, it was working, it just wasn't showing up. So let's get rid of all that other nonsense. So we've got a picture that we need to draw. We have a point chosen at random inside the square, so the probability it lies in any region is equal to the area of that region. Quite a common idea. We're basically, often the example is with randomly throwing a dart at a dartboard. In here, it's a square dartboard, and we always hit within this square. The bigger the area we're aiming for, the more likely we'll hit that area. R then is giving the random variable as distance from the origin. So the thing to notice is our origin is down here, so our x values go from 0 to 1, and our y values go from 0 to 1. So R is a random variable at the distance from the origin. So if I randomly hit this point here, then my score would be the distance, the straight line distance back to the origin. And a really clever technique for this is not to work out the probability of hitting an exact distance. This is a continuous distribution, so hitting any exact value is actually going to be 0. But instead, thinking about hitting anything up to that particular value. So we're actually having what's called a cumulative distribution. Think cumulative frequency, it's a up to that value. And that's exactly what the question is wanting us to show. Show the cumulative distribution function, which is given by that, is that stuff. And in particular, that's only when R is bigger than 1 and less than root 2. So what exactly does that mean for my picture? Well, 1 is this value here. And anything less than 1 is actually going to be really nice because it's just a semicircle, and we can work out the area of that semicircle, and that gives you the distribution. And you can see that the second half of this question is exactly that. I kind of want to do the second half first, but I'm going to hold out. But I know that that second part will actually be really pleasant. The unfortunate thing is when that R gets even bigger. The root 2, just so that you're aware, is this distance here. So we can't, as soon as it's bigger than root 2, then we cover the entire square. So it's really dull in that regard. So what we're really wanting to do, and I drew my square slightly too high up, is we're saying that this distance here is now R. I could just label it with a y coordinate of R, an x coordinate of R, and I want the semicircle drawn relatively well. So I want to find this area here that's inside my square and inside that semicircle. So I'm going to call that area A, and that's what I'm looking for. How am I going to find that area comfortably? Well, it feels like I want to do the area of the whole semicircle. And if you do look at the answer, the area of the whole quarter circle, is exactly that term there. And I want to lose this area and this area? Well, there's going to be quite a bit of symmetry that I can employ here. So let's label some stuff on. I'm going to call the origin O. I'm going to say that this point up there is A, B, and C. So I would really quite like to find the area of the weird shape ABC. I'm going to draw that separately as well. So you've got the origin. You've got a point C, which is 1 at distance of 1. You've got a point R, at distance of R, a point which I'm calling A. You've got an O to B, that's at a distance of R. And then we've got this arc here. And what I want, I'm going to put the C in a slightly better place now, is this area at the end. So nice thing is, what else do we know? We know that this side here is 1. We probably want to find that angle at some point. We know the whole sector has a particular value. So let's start finding some areas. So the sector AOB is going to have an area of theta r squared, provided that I'm in radians. Now, it doesn't say anywhere, but I'm going to insist that I'm in radians for theta in radians, and I've lost the half theta r squared. I don't know what theta is yet. I can certainly work it out. I should probably do that earlier rather than later. We know that cos theta is adjacent over hypotenuse. So the theta is cos inverse of R1 over R, which I'm writing it in that way because the question's written it in that way. Brilliant. So that gives me my angle. So that gives me my area of the sector, therefore is a half R squared cos inverse R inverse, which again is really promising because that is this term here once I double it up. But that's not the region I want, that's the sector. So I also need the triangle OCB. And there's probably lots of different ways I can try and work out what this triangle is. I could do a half AB sine C, but then I'm doing sine of this angle, and sine of cos inverse is not going to be pleasant. So instead, I'm going to find this CB side. Pythagoras says that this squared plus 1 squared gives the last side squared. So a bit of reverse Pythagoras gives that as r squared, the square root of r squared minus 1. So therefore the triangle OCB is a half root r squared minus 1. So then it's not really a segment, but the shape, the area of ABC therefore is the entire sector minus that triangle. So now the area, should I label more stuff, or should I just give this a fancy name? I'm going to give this a fancy name. I'm going to give it the script letter A. So now the area A is given by the entire quarter circle minus 2 lots of that area ABC that we've just worked out. And quite promisingly, we've got a minus minus giving the plus that the question gave. So this is, let's put it in the order that the question's given it as well. So this is root r squared minus 1 plus minus. And voila. And the whole reason of doing that, this is exactly defined as the probability that we're less than or equal to r for 1 less than or equal to r less than or equal to root 2. Nice. A quick double check that I haven't done anything too stupid, because there's a few things in here that could have been awkward. Now, it is a show that question, so it's not going to be a problem. But this here, we can't square root a negative, which is why that r has to be greater than 1. And over here, we can't cos inverse something bigger than 1, which again is saying that the r has to be bigger than 1, so 1 over r is less than 1. So all of that holds. And then finally, what I thought was the easier part is the case when the r is less than 1. So if r is, and I should actually give it its proper bound, 0 is less than or equal to r is less than or equal to 1, the probability of r being less than or equal to r is equal to the area of, and now what is the script b? The script b, if I'm trying to keep my notation, is something a bit like that. So that's this area here in my picture. And the area of that is just simply 1/4 pi r squared. R's not got big enough to cause any problems. Okay, so that's part I done, which really is just a geometry question at this point. Part 2 then. Part 2 is now wanting the expected value of r. And expectation has a particular formula. In the previous question, we used it as the sum over the values of the value times the probability of that value. Now, that only works in the discrete world. And if you know anything about summations, when you make a summation continuous, you actually get an integral. So we're actually integrating over all the possible values of r times the probability that r is less than or equal to r. And that's quite a nice little formula for us to manipulate. And I do just want to check, because it might not be a less than or equal to. And I do want to check. This is, I've just got the textbook open to remind myself of the formulas, because of course I've not used these formulas in an exceptionally long time. And as in the same way that you've probably never seen these formulas. Let's have, I want continuous distributions, and I want their formula for the expectation, and it is using the PDF, not the, okay, so this does need to be the equals version, in the same way that the summation was the equals version. So I do need what's called the PDF, the probability density function, not the cumulative distribution function. And we can get that fairly nicely, although I'm looking at the function and I'm not particularly enthralled by the idea, but this thing here, which is often called f of r is the derivative of the cumulative distribution function. So we get that statement there. I do just want to confirm that a bit more than my own memory, but I'm not finding the right place in the textbook, so I'm going to look one more place and see if I can confirm or deny this fact. So this fact is true, so I found that and I can confirm that, and I've already confirmed, yep, and there's the other statement as well. Okay, so we need to both differentiate this p less than or equal to r function, and we need to then integrate it with this extra r that pops in, which isn't particularly nice at all. And one thing to notice is in the solution we've only got the limits of 1 and r, but really we should be integrating all the way from 0 to integrating from 0 to root 2, because that's when we've got a non-zero probability. So where has the integral from 0 to 1 gone, and are we worried about it? Right now I am a little worried about it, but let's go ahead and find this function first. And one thing that I really don't like about this is we're going to have to differentiate that term there. So we can differentiate at least the first region. So that's for 0 less than or equal to r less than or equal to 1. So that region was particularly easy to differentiate. The next region, if I differentiate this term, that's to the power half. A 2r pops out, so that's going to be r. The half goes down to a negative half. So that term differentiates to r over r squared minus 1. Quite pleasing, because that matches with at least the denominator of what I'm trying to show. Plus a half pi r for that second term. And now for the really awkward term. How do I differentiate cos inverse of r inverse? And that isn't pleasant at all. We do have some rules within the formula booklet that will help us out. So we know, and I'm going to do some little scribbles over here. We know that cos inverse of x, the derivative of that, is given by negative 1 over the root of 1 minus x squared. So if I want to differentiate cos inverse of 1 over, and I'll leave it into r minus 1, that's going to mean that I'll differentiate it ignoring the fact that it's unpleasant, and then chain rule says to times by the derivative of the thing that made it unpleasant, which is 1, which would be negative r to the negative 2, as so. And that we can simplify a little bit by pushing the r squared, maybe not the entire r squared. Certainly the negatives cancel. I'm going to push one of the r's under the square root, and we get that. And now to differentiate this, we need to product rule it as well. So we've got minus r squared times by the derivative minus 2r cos inverse of r inverse between 1 and root 2. I'm going to move that other statement over as well. So that's my probability density function, my FR. So now R is the derivative, the expectation of R is the integral of this thing times by R over the limits. And it's not pleasant at all. I am going to do one thing here. Cross out the R, cross out the R. And it's really, really unpleasant because this thing is going into the integral. And I really don't want that thing in the integral at all. Because I don't know, because there's no thing of that in the answer. So is there something which somehow manages to make that cancel out? Maybe. We don't know yet. So now let's go for it. Let's go for E of r is therefore going to be the integral, and we need to split it into two parts, the integral between 0 and 1 of the half pi r times by an extra r, plus the integral between 1 and root 2 of all of that nonsense. Now, one thing that does happen is that cancels with that, which I would say is very surprising, but these things are often quite symmetric. So we have the half theta r squared minus 2 r squared cos inverse r inverse dr. So we have some things that we like, and then some things that we really, really don't like. Because we can evaluate the half pi r squared things, and they actually combine really nicely because they're both the same. I could just integrate the half pi r squared between 0 and root 2. But then the other term, how is the other term linked to what we have there in any pleasant way whatsoever? Because that term looks almost like if we didn't have this r squared. If we didn't have this r squared here and we didn't have to product rule, we'd get the cos inverse leading to this term. We'll times it by r, and then the r squared pops back in afterwards. So that feels like what would happen if you didn't know the product rule. I just want to have a quick double check that the r's did cancel in the way. I do only need to use one of these r's to go under the square root. Yeah. So I'm a little worried again, but I'll take a couple more logical steps before I pause for too much. So this can become a 6th pi r cubed between 0 and root 2, not root 3, cubed between 0 and root 2 for those, minus the integral, or minus 2 lots of the integral of r squared cos inverse r inverse dr. Because our other option is we could make a substitution. We could do some kind of substitution to hopefully change that integral into something more pleasant. The other issue is this is an additional term. We're adding something on here, but the ER term isn't adding something on. It's an extra multiplying factor, a 2/3 multiplying. And that term at the front certainly isn't 0. So maybe I want to keep that. Or when I do the substitution, another term pops out. Or I'm going to do an integration by parts, because I can differentiate this term happily. I think that's it. I think it's an integration by parts on that term. And if you spotted that before me, well done. I am going to evaluate that first part. So putting the root 2 in is going to give a 2 root 2, which cancels partially with the 6th. Something the 0 in does absolutely nothing. Minus 2 lots of, and I'm debating how I want to do this. I think I now just want to open a big square bracket and do my by parts. So I want to differentiate the cos inverse r inverse, and I want to integrate the r squared, which is giving me a third, which I didn't have before, a third r cubed, and u dash is the thing that I had before, 1 over r root r squared minus 1. Okay, so then this becomes a third r cubed cos inverse r inverse between the limits of root 2 and 1. So I'm going to have to think carefully about what that does, minus the integral between 1 and root 2 of those multiplied together, which is r squared over 3. Okay, it's really close to their answer now, provided that this thing evaluates to exactly cancel this thing. So let's do it. So this is still root 2 over 3 pi minus 2 lots of, when I sub root 3 in, when I sub root 2 in, I've got 2 root 2 over 3 cos inverse of 1 over root 2, which is pi by 4. That's pleasing. Minus, when I sub 1 in, that's a third. Cos inverse of 1 is just 0. And that's really, really pleasing. Plus 2/3, the 2 from the outside of the square bracket and the 3 from the inside, the integral between 1 and root 2 of r squared over root r squared minus 1 dr. None of my brackets have gone haywire. Now just mentally check that this term here is exactly what I want. Yep, the 2's cancel with the 4, so they all cancel out perfectly, and I'm left with 2/3 the integral r squared over root r squared minus 1 dr, as required. A very pure piece of work there. The only stats that you really needed was these two facts here, which is why I liked these stats questions. They are just bonus pure questions hidden under a little bit of stats. Next then, show further that ER is actually this. So it's actually telling us now to evaluate this integral. So let's give it a go. So this is now part 3. We currently have that ER is 2/3 of the integral between 1 and root 2 of r squared over root r squared minus 1. And a couple of things which I'm going to try and notice straight away. First, this ln suddenly feels a bit out of place, except if you remember your integrals, you know that integrals of the form 1 over the square root of r squared minus 1 integrate into a cosh inverse, or equivalently into a ln of something plus a square root of something. So I'm seeing this, and I'm really wanting this to be 1 over. So I'm going to do something a little bit silly, and you might be shouting at me that I haven't put my dr on the end yet, because I haven't finished here. I'm going to write this as r squared minus 1 plus 1. So I'm going to include a plus 1 minus 1, and really what I'm doing here is a style of... actually, do I want to do this? Because I'm just in anticipating what one of those will be. I'll finish writing it out and then we'll discuss further. I'm kind of doing the partial fractions here. I'm splitting it into its different components. Now this first term over that will be left with r squared minus 1 to the power of a half. And that term I don't think is going to be very nice. Plus 1 over the square root of r squared minus 1 dr. Now, if this first term had an r in front, I'd be really happy, because then it's just an integration by recognition. Because it doesn't, it's actually quite unpleasant. And, well, this term is now dealt with. This will go to cosh inverse of r, which will likely lead to something that looks like the ln root 2 plus 1 term. But this I now don't know how to deal with. But I still want to use that cosh inverse idea. But now I'm going to try and think if I can use it in another marginally more silly manner. And I'm actually taking inspiration from what we did over here, where we actually had 1 minus r to the minus 2. If I could use that and have the derivative of that appear, then maybe this is an integral in another direction. So I'm going to write this as 2/3 integral of, and then I'm going to factor out an r squared from the thing in the denominator, so that's 1 minus r to the minus 2 with an r squared on top. Is that going to help me out in another manner? Well, no, because that cancels, that cancels. This is now looking more like a cos or a sine inverse integral, which is a lot less pleasant because sines don't lead to lns. And it would need the derivative of r to the minus 2 to appear, which looks like r to the minus 3, which I just don't have. So again, that didn't look like it was going to be helpful. But I still really want to use the cosh idea. So my final plan, and the one that I think I'm going to run with without pausing and coming back to, is a substitution. So I'm going to let r equal cosh u. If this was 1 over, this would be how you would derive this integral, but it's not 1 over, so I'm going to do it this way and hope that things lead nicely into what I want. So this is going to be 2/3 the integral of, I've then got cosh squared u on the top and the root of cosh squared minus 1 on the denominator. I want this to become a du, so I need to work out how it's going to become a du. So dr by du is sine u. Lovely thing about hyperbolics is they don't swap sign when you differentiate. So then which way round is exactly the right way round? We want a sine u du. Our limits, so when r equals 1, u is cosh inverse of 1, which is ln of 1 plus the square root of, cosh inverse of 1 is just 0. So I was trying to go too deep into that. If you think about the cosh curve, it's just 0. And then when r equals root 2, u is cosh inverse of root 2. This one I do need the formula, so this is going to be ln of root 2 plus the square root of root 2 squared minus 1, which is just ln of root 2 plus 1, which is quite pleasing because that's in the answer. So my limits, my bottom limit is 0 and my top limit is ln root 2 plus 1. So let's keep going. Let's see what this manipulates down to be. This is going to be 2/3 between the limits of root 2 plus 1. The denominator of this, cosh squared minus 1, is exactly shine. Or is it negative shine? It better be positive shine. Cosh squared minus shine squared is equal to 1. So yeah, it's positive sign, which cancels with the sign that we have. So I'm left with cosh squared u du. I now have a choice. I can try and use some hyperbolic identities, or I could rewrite this in terms of exponentials. I've got a feeling that I want to use exponentials, because the nice thing about exponentials is when I sub these things in, they just do nice things. So I'm going to go into exponentials here. So cosh itself is a half e to the x. I'll do that side over here. So cosh squared u would be a quarter e to the x plus e to the minus x, not x's here, u's. U minus u squared. So that's going to be a quarter e to the 2u plus 2 plus e to the minus 2u. So over here, this is now going to be the integral of 1 over 6. I'm pulling that quarter out of the way. Excuse me. And this is the integral between 0 and stuff of e to the 2u plus 2 plus e to the minus 2u du. And if you do see these two terms together, your mind does think this is a cosh 2u situation, but I want to leave them as exponentials for the reason discussed a moment ago. So this is going to be a sixth. We can integrate each of these quite easily. E to the half e to the 2u minus a half e to the 2 minus 2u plus 2u between the limits. I was just worried that I'm getting a third on that term, but the answer does have a common factor of a third in there. So I'm still pretty happy. I do want to work out what 2 ln, what's 2 ln root 2 plus 1 is, because I'm subbing that in and that's going to be the power. I'd really like to write this as ln of, that's root 2 plus 1 squared. So that'll be ln of, is it 3 plus, which is marginally worrying because I don't have a 3 plus root 2. I've got a 1 plus root 2 in my answer. Am I worried enough? Maybe. I'm just going to double check. Oh, that's plus 2 root 2. Yeah, I was right to be worried a little bit at least. And then minus 2 ln root 2 plus 1 can be written as ln of 1 over 3 plus 2 root 2. Let's try and rationalise that. There'll be 3 minus 2 root 2 on the numerator, and the denominator will become 9 minus 8. It's just 1. That's quite a common, well, it's a general fact actually for these cosh inverse style ln terms. So let's put everything in. So we have here, this is going to be a sixth of, when I sub the ln term into that first, oh, there's a half. No, that's, I was excited for a moment, but that's not quite a valid excitement yet. So I get that. When I sub it into the other one, I'm getting minus a half ln 3 minus the root 2 plus 2 ln. Oh, I was right to be unworried because this is where my ln term is coming from, not from the other things. So I'm hoping actually these become non-ln terms. Maybe they will. Let's keep playing and see. I'm actually starting to think that I wanted to leave this one as a power of -1 inside the ln, but I'm getting distracted and ahead of myself. So then minus when I sub in the 0. So when I sub in the 0, I get a half minus a half plus 0. So that doesn't do anything. So I have a sixth of a half ln, well, I want to factor that half out of these two terms. And actually, yeah, the power of half is going to square root this thing, whereas over on the side I squared it already. So that there's some doubling up of work going on here. But this we can write as ln of 3 plus root 2 over 3 minus root 2. Because we're subtracting the lns, and that little half in front is just a common factor to both of them, so that's fine. Plus 2 ln root 2 plus 1. Now, this thing is going to be, what's the nicest way to deal with this? I could try and have I lost a 2 root 2? Yeah, it's a 2 root 2. So there should be 2's in front of these. And close the bracket. Best way to tackle this, so I've got choices. I can bring the power of a half in. I'm not liking the fact that it's got a ln there. Oh, what am I doing? When you put a ln in, when you put a ln into an e, it destroys the ln. That was the whole point of writing it like this. So these two terms here are way simpler than I was trying to make them out to be. Thank you for screaming at the video of what a fool that was. So this is a half 3 plus 2 root 2 minus a half 3 minus 2 root 2. So that's going to give me a half of 3 minus a half of 3. They cancel. I've got a root 2 minus a minus root 2. So this is a 2 root 2, and we're done. We can factorize out that 2 to cancel down to a third on the exterior. And we have exactly the simplified version as expected, as required. So, and actually an exceptionally pure question. We delved into hyperbolics, into inverse trig. We did quite a lot of geometric work in the first half of the question, a lot of integration. We used substitution and we used by parts. So a very heavy pure question despite being in the stats world. But if you can get through the statsy, then this question was difficult, but not impossible. And hopefully it was particularly useful to you. If you do spot any other tricks that you did that I didn't, any other things to become more efficient in this problem, I know certainly this section here could have been made a lot more efficient if I noticed what was actually going on with some of the substitutions. Please do let me know. Otherwise, I hope this playlist was particularly helpful, and good luck with the rest of your step prep.